Okay, so now we are going to solve this example, example 2.5, which is a very, very important example. It summarizes the importance of this algebraic method, how valuable, how useful this algebraic method is. And the problem is the following. We have to obtain the expectation value, the mean value, now the average, of the potential energy. So let's write the potential energy. We are talking about the harmonic oscillator. So this is the operator for the potential energy. We have to find the expectation value for this potential energy in the nth stationary state of the harmonic oscillator. Okay, so how can we get this expectation value for any general psi n? If we try to use the old procedure of solving the integrals for the Gaussian functions, we have to do it for each psi 0, not the ground state of psi 1. But here, we want to do it in general for any possible psi n. And how can we do that? Using the algebraic method. And so let's write the equation for expectation value. So we put it here. We have psi n complex conjugate, then the potential energy psi n. So this is what we want to solve. Well, if we are going to do for a specific wave function, solving using integrals of Gaussian, using integrals of Gaussian functions, you need a specific psi n. But we want to do this in general, any psi n. How can we do that? So let's go on writing what we have to do. We have this, I'm going to write the operator for the potential energy. So 1/2 m omega squared. I put this outside the integral because these are just constants. And what survives there is the x squared. Well, so if psi n was for a specific value of n, you would solve this integral using what you know about Gaussian function. But we want it for any psi n. We don't need to specify. We don't want to specify. So how can we do that? Well, let's remember the definitions of the ladder operators. So the A plus is 2mh bar omega, all this in the square root. Here we have minus IP plus m omega x. All these are operators, so if you want to be very precise, you put the heads there. And the A minus is similar, but the sign changes. So 2mh bar omega square root, and here we have plus I momentum operator plus m omega x. And as we said, these are all operators. Well, how can we use this knowledge to solve this integral? Very well. Look, if we sum these two lines, we can find an equation for the operator position in terms of A plus and A minus. So what I'm saying is I'm going to sum these two lines, and I'm going to find an equation for position. Because if I sum these two lines, you see that this term and this term cancel. So A plus plus A minus is equal to 2m omega x, and what we have in the denominator. Correct. Well, here we can also do some simplifications and put the square root. See, we have here 2 and 2, so I can put in the numerator the square root of 2. Well, we also have m and m, so I can put the m in the numerator. I can also do the same for omega. And below we keep the h bar. All that are a prefactor in front of x. So in other words, I can write that the operator x is the square root of h bar divided by 2m omega, and the sum of these two operators, the raising operator and the lowering operator. How can this help us solving this integral? It can help us a lot. So what I'm going to do now, I'm going to bring this up. So let me erase what we have in between so you can better see what we are going to do. So we are going to bring this. So we are going to rewrite the expectation value of the potential energy as, well, that constant that we already had. Now, wherever we find this x squared, I'm going to use this equation, okay? So that means this square root disappears, so I have h bar 2m omega, no more square root. And inside the integral, we have psi n complex conjugate. And now let's do the square. Careful with the order. Okay, so I'm going to do the square here. A plus plus a minus, a plus plus a minus. And so we have to be careful because we are dealing with operators. So if we are dealing with operators, we have to go one by one. This term becomes a plus a plus. Okay, the other one, this term becomes a plus a minus. Now let's pick another term. This one becomes a minus a plus. So you see, I'm being very careful here. This term is not the same as this term because the order is not the same. So you have to be very careful here when you're doing these multiplications of operators. And then finally, the last one, a minus a minus. And now, this is what we have to solve. Okay, all right, so let me remove this from our way. We already understood this part, and let's continue. Well, let's first look at these constants in front of the integral, see what we can simplify in this story. So we have this mass that is gone, one of these omegas, and so this becomes h bar omega divided by 4. Good. So now let's go term one by one on those terms above. Well, first let me discuss with you what is a plus acting on psi n. We found in one of the previous videos that this is square root of n plus 1 psi n plus 1. So what I'm thinking is about this term here. Well, this term has another a plus, so let me multiply again, act again with this a plus. And now we have n plus 1. Now, acting with this new a plus on this psi n plus 1 gives us square root of n plus 2. And we end up with psi n plus 2, okay? All right, so then I'm going to put this in our first term there in that integral. So we have, get some space here. We have n plus 1, n plus 2, all that in the square root, psi n plus 2. So this is the first term. Some of you may already see that this is 0. This is 0 because n and n plus 2 are different. And we said that the solutions are orthogonal when the indexes are different, when we are dealing with different stationary states. So this integral is 0, okay? So we can already cancel this guy, okay? All right. All right, so what I used here is this property that if m is different from n, if m is different from n, this is 0. So, and that's exactly what we have above. N is not equal to n plus 2. All right, so this first term is gone. All right, so now let's look at the next term. This next term here. All right, so what do we have for that next term? Well, let's start with A minus, no? Because this is the first one that is acting on psi n. So A minus of psi n, we learned that is square root of n psi n minus 1. Okay, now let's put A plus acting on A minus psi n. And so this means A plus acting on psi n minus 1. That's what survives in this story, which means square root of n, and again, square root of n. And we are now go up. Okay, so this second term, I'm going to write it also as an integral here, became square root of n with square root of n became n, which I can put, so just a constant, so I can put inside outside the integral n, and what survived inside psi n complex conjugate, and this psi n dx. Okay, so this is our second term, and this is good because by normalization, we know that this integral is 1. So this term survives. Okay, so we have there n that is going to survive. Okay, let me remove this, and now we are going to think about the third term. Okay, so now we are going to study this term here. Okay, so this term there is, first we have A plus adjunct psi n, and this raises it, so we get psi n plus 1. But we also have A minus, so A minus acting on this whole thing means A minus now acting on psi n plus 1, so it brings it down. It brings it down, and we have n square root of n plus 1, square root of n plus 1, and psi n. This is also a good one. So that dark blue term, the third term, becomes here plus n plus 1, it's a constant, and inside the integral we have again psi n conjugate psi n, because it's psi n dx. Which, just as this term here, the light blue, this term, the dark blue, well, is again by normalization, this is 1. So this term also survives. Okay. Now let's see the last one. So the last one, I'll put it in red. So now let's see this last one. So what we have in this last one, we have A minus. Now, so let's see, A minus acting on psi n gives us square root of n psi n minus 1. And now I put A minus again, and we have n minus 1, and bring it down, psi n minus 2. So let's copy what we have. Again, we have some constants that we can put outside the integral, and we have n minus 1, all these in the square root, and what survives inside is the psi n complex conjugate with psi n minus 2. This is n minus 2. Again, just as we saw above, the first term, this term also cancels by orthogonality. So, yes, clear. So, what survives in this whole story? What survives is the first term was gone. The second term gives us n, because by normalization, this whole thing is just 1. The third term, the third term gives us n plus 1, because by normalization, this thing is just 1. And the last term, this one, is 0. So that's all that survived. So let's rewrite this. We have h bar omega over 4, 2n plus 1. So we can write this as h bar omega over 2n plus 1. So this is our answer. Let's write it here again. Expectation value of the potential energy is h bar omega over 2 n plus 1. Why did we write in this way? Because it makes us see something very interesting. Remember what is the energy of each one of these stationary states for the harmonic oscillator. The energy is h bar omega over 2 n plus 1. See? So you see that the expectation value of the potential energy is just, sorry, I wrote it wrong. I wrote everything wrong. Let me correct what I did here. Here there is a half. Now this is good. Because, you see, this was 4. So 2 with 2 is 4. So this is good. And this first term, 2n, 2 divided by 4, gave us just half. So this is good. So let me rewrite this like this. And now let me rewrite properly the equation for the energies of the stationary states, now for the harmonic oscillator. We found that the energy of each state, psi n, is h bar omega n plus half. So we put in this form just to be able to say, look, the expectation value, write it here, the expectation value of the potential energy is half the energy of the stationary states. Yeah, so this is an interesting relationship that we found. Where is the other half? Then I let for you to compute. The other half is the expectation value of the kinetic energy. Okay, if you go through the same procedure, you see that the expectation value for the kinetic energy is again that same result that we got for the potential energy, which means it's also half of the energy of the state. Now, how are we going to compute, or I'm going to let you compute, how are you going to compute this potential, the expectation value for the kinetic energy? Same thing as we did for the potential energy. What we need to remember is that kinetic energy is p squared over 2m, right? So you have to go back to the equation for A plus and A minus. Let's rewrite them here. A plus has minus IP, and A minus has plus IP. So now what we want to obtain is, playing with these two equations, subtracting now these two equations, we are going to find an expression for the momentum in terms of A dagger and A minus. So if you go through this procedure, please do that. You'll find that this operator can be written like this. I, and then square root of h bar m omega divided by 2, a plus minus a minus, okay? So with this, you can then obtain the expectation value of the kinetic energy, just as we did for the potential energy. And you're going to find the same result. So potential energy and kinetic energy, each of them is half of the energy of the total energy of the state. Now, let me come back here to show to you something interesting. Now, I don't know if you notice. So let me get some space so it's not too crowded here. So look carefully at what we wrote here. So what we conclude is that the only terms that can survive are the terms where we have an even number of A minus and A plus, an even number, an equal number, sorry, an equal number of A plus and A minus, because an equal number of A pluses and A minus, they may raise and lower so that we always go back to psi n. So equal number of A plus and A minus are the terms that survive. If I don't have equal numbers of A plus and A minus, we are going to end up with a state that is not the psi n. No, so this is the case of A plus, A plus. We have two A plus, but no A minus. So this takes us to an n plus 2, which is not, which is going to cancel. No? If I put A minus, again, this is going to take us to a different state, different from the psi n. So they are orthogonal and they will cancel. Now, so let me repeat. The only terms that survive are the ones that have the same number of A plus and A minus. In this specific problem, it was 1 A plus and 1 A minus, good, it will survive. 1 A plus and 1 A minus, good, it will survive. Okay, so that's the end of this video.